of the classification theorem. We probably won't get to all the details of both of them, but maybe I'll give you some idea how it's done. Okay, so the proof of number one, and this was to remind you. So here we're assuming that phi is hyperbolic. Then phi has a representative f from gamma to gamma, and delta is f invariant. Slopes are equal to lambda on delta and less than lambda on gamma minus delta, and then delta has an invariant f invariant train-track structure. Okay, that was what number one said. So given, just starting from the assumption that phi is hyperbolic, we have to find a particularly nice representative that has this train-track structure on a subgraph. Okay. And in fact, we'll show that every point in the min set can be approximated by something like this. So all the moves. So we'll start, because phi is hyperbolic, the min set is non-empty. So you start. So let gamma be in the min set of phi. Okay, because that's non-empty, I know I have something. And so the proof will approximate gamma. So we'll approximate gamma by representative as above. So all moves are going to be perturbations. Okay. Okay. So we have f from gamma to gamma. Okay. This is the representative on gamma. Right. So this is the representative on gamma, and the larger slope is lambda, where d phi is log lambda. This is because it's in the min set. Right? The displacement is log lambda, so I can find some element, or any element in the min set will satisfy this. I have a change of markings map where the larger slope is lambda. Okay, and from last time we know that whenever we have a map like this that realizes the distance between the source and the target, then there's a tension graph, and I can approximate. After approximating, I can assume that the tension graph has a train-track structure as well. So after approximating as last time, we may assume that that gamma has the tension graph delta phi. So this is a simply union of edges where the slope is equal to lambda. But moreover, we have a train-track structure that has a non-degenerate train-track structure. In other words, if there is a vertex with one gate, then we can approximate and get rid of it. That has a non-degenerate train-track structure. Okay, so that's kind of a starting point. This is true for any map that realizes the distance, that minimizes the slope. After perturbing the map slightly, we can assume that there is a tension graph with a train-track structure. Okay. So I'd like this graph to be my desired graph delta, right? So I'd like to know that, for example, that it is f invariant, that f of delta is contained in delta. So what if it's not? So okay, so step one, maybe I'll just call it delta for simplicity. So arranging f of delta is contained in delta. So suppose suppose E is an edge in delta, and f of E is not contained in delta. Okay, so there is some edge in delta that slips out. Okay, so what can I do? Okay, so here's what I want to do. I want to scale the metric up on delta and down on the complement of delta. So scale the metric on gamma up on delta, down on gamma minus delta a tiny bit. Just by some very small epsilon. So you just make it uniformly larger. You multiply by some constant slightly bigger than 1 on delta, and by some constant slightly smaller than 1 on the complement of delta. You can do it so that the lengths still add up to 1. So then what happens? So what happens to E, for example? No. So first of all, what happens to the slopes? If I start with some edge, any edge in gamma, what is the slope of the new map? I'm still taking the same map, but I'm wondering what is the slope now? Right? If I take some edge in E, in delta, that maps all the way into delta, well, the metric on delta was just scaled, so the slope will still be lambda. But if it's mapped into the complement, then E was scaled up, but the complement was scaled down. So now the image is shorter than before, but the edge is longer than before. So that means the slope goes down. So the slope on every edge is still less than or equal to lambda. It is strictly less than lambda in the complement in gamma minus delta. If you start out with a slope less than lambda, and you do this tiny bit perturbation, it'll still be less than lambda. It might go up maybe. If some edge from the complement maps into delta, then the slope on that edge will go up. But it started out being less than lambda. So when you approximate, it'll still be less than lambda. But it is less. It is also, so the key point is that it is also less than lambda on E. Because E is in delta, so it got scaled up, but its image did not get scaled up by the same factor. So the slope went down. And so that means that the tension graph decreases. So the tension graph decreases. Okay. Now when this happens, you may acquire new points with one gate. Right? So you started out with some nice little train track, like this, but then maybe this edge got erased, right, from delta, and so now you just have one gate. So then you may have to go back to the original move to perturb F to get rid of the one gate points, but that can decrease delta even further. So if vertices with one gate appear in the new delta, go back to this first step, or a zeroth step, to clean up. I'll just call it cleaning up. So this decreases delta further. It can never become empty, right? Delta can never become empty, because that would mean that that you have that your displacement wasn't dphi but smaller. Okay, so repeat this. Repeat these operations until you arrive at a representative, which I'll still call f from gamma to gamma. It should probably be gamma prime or something like that. Some new name, but anyway, let's just call it f. Where the tension graph delta has no gate one gate points, and f of delta is contained in delta. Right. So the point is that if this doesn't hold, then you can perturb and get smaller delta. Okay. So the idea is to decrease delta as much as possible. Okay, now step 2 is to arrange that f preserves the train track structure. Step 2. So here, arrange that f preserves the train track structure. You see, in this zero step, the one that the cleanup operation, we did not change gamma at all. Even the metric, gamma stays the same point. We just perturb f. In this step, we don't change the topology of gamma. We just perturb the metric, and then maybe also the map f. In here, in step 2, we'll actually perturb gamma itself. Okay, so this will require changing the topology of gamma. Okay, so there are several issues with not, why does f not preserve the train track structure? This is the train track structure you have from the tension graph, right? You're declaring 2 points to be, 2 directions to be equivalent if they map to the same place, right? So this is the usual tension. The train track structure is the usual one on the tension graph. So in other words, d is equivalent to d prime if and only if f star d is equal to f star d prime. Here I'm not iterating. I'm only thinking of this as we only have a map. We don't have a train track. You only want to iterate if you have a train track map. Okay, so what can go wrong? So for example, I could have an edge and its image is not legal. Okay, so say E in delta is an edge, and f of E, which is also in delta. I mean, this is some path in delta, but it may not be legal. In other words, I have this edge here, E, and if I look at the image, it somehow crosses some illegal turn. Right? It's some kind of edge path, right? It's some kind of a path, but there is a point where it crosses an illegal turn. So there are these 2 directions, d and d prime, that are equivalent in this train track structure coming from the tension graph. Okay, so now what I want to do is fold d and d prime. Okay, so change gamma by identifying small intervals of the same length in the directions d and d prime. right? So this f of v crosses this illegal term, so it takes a little interval on one side to and interval. I mean the map f. This is also f, but the map f takes these two directions and sends them to the same direction. This is f of d. F of d. What's f of d prime. So what I want to do is change gamma by identifying these two directions. This is really, I mean, the picture you should imagine is the example I started with today with the train track structure for A goes to B and B goes to AB. There was an illegal turn, and we constructed the whole min set by folding this illegal turn. So that's exactly what we're doing here. We have an illegal turn, and we're folding it, and we get another graph. Maybe it's in a different simplex, right? If there are several edges here, it's like this is now valence 4. After folding, this will become, you'll have a valence 3 vertex that you didn't have before. So this is like being on the face of a simplex and then going inside the simplex, inside the bigger simplex, because you'll have more edges after this fold. So you're not staying in the same simplex. It's not just a matter of changing the metric. You're actually changing the topology of the graph. Okay, so gamma prime here is going to be gamma modulo this equivalence relation, where we have, well, I don't know, whatever the, here. It doesn't matter. So you have two of these directions, and then you're folding. So this is gamma, and then gamma prime is going to be obtained by identifying these red segments, like this. I don't know. Like that, right? And the point is that f induces a map. So there's gamma, there's this quotient map, and we had f here, there's an induced map f prime. Why is there an induced map? Well, because f respects this equivalence relation, right? We're identifying these two segments, but they have the same image under f. So there is a well-defined map from gamma prime to gamma prime. And this map still has the same slope on all edges. So f prime still has slope lambda on delta prime, which is the image of delta, and slope less than lambda on other edges. Okay, but now what happened to this edge E? Where does it go now? After this identification, my picture is like this. This is the picture in gamma prime. Well, the image of E now it backtracks, right? It goes to this red and then it comes back. So I can homotope the map and reduce the slope, because the image now is going to be smaller. But f prime restricted, so on backtracks on the image on the image of E. So after a homotopy, the tension graph decreases. You're going to lose this edge that comes from E, because it no longer has slope lambda. It now has smaller slope, so it drops out of delta. And again, you can create vertices with one gate, and so you have to go back to these cleanup operations, and then maybe even this fails after that, so you have to repeat this step as well. You always have to go back and clean up all the steps you did before. But in all these operations, the delta goes down. What else do we need to arrange for to make sure that f preserves this train track structure? Well, we have to know that legal terms go to legal terms, right? So if I take a pair of directions that they're not equivalent in delta, then I want to know that the images are also not equivalent. So what happens? So say D and D prime are inequivalent directions. Directions at a vertex of delta, but f star D is equivalent to f star of D prime. In other words, I have some vertex in delta. This is picture in delta. I have a legal term here, but somehow f sends this to an illegal term, like this. This is f of b over here. Right? So what do I do then? Well, because this is an illegal term, that means that f is going to identify this. These two image directions are equivalent, meaning that f sends them to the same direction. So what I can do is fold again. So fold f star of d and f star of d prime. And as a consequence, so then the original two directions, d1 and d2, or d and d prime, become equivalent. D and d prime become equivalent. So what happened here was that we didn't at this point we didn't change the tension graph, but the train track structure became simpler because this is going to reduce the number of gates. These two gates were distinct, but now after this operation they become the same gate. And so I guess in topology, in proofs like this, what you really want is some notion of complexity. You want to make sure that when you're doing all these operations, you're not making something else more complicated, right? You simplify this, but you make something else more complicated. And you have to go back to fix that, but maybe when you're doing this other thing became more complicated. So you need a notion of complexity, and then you argue that all your procedures decrease the complexity. Or actually, an elegant way to say the proof is to say, well, find an object with minimal complexity and argue that it's good, and then this becomes maybe more, maybe you like the proof better that way. Okay, so the point is there is a notion of complexity that always decreases. And it's kind of if you're used to this kind of stuff, then it's not unexpected, but it does. Let's see, it wrote it down somewhere. Okay, and the complexity is this. It's you have the complexity of delta, which I'll have to tell you what it is for a graph. What is the complexity of a graph? And then there's the complexity of the train track structure, and then the last one is the number of edges in delta. Somehow this is the one that decreases when you in that cleanup operation, right? When you're just changing the map. If you have a point with one gate, delta could have it could be some graph with some hanging trees, and you're removing these trees. Okay, so that reduces the number of edges, and it will leave these two things alone. So this is a triple of numbers, and you're ordering it lexicographically. Each of these numbers can have only finitely many possible values. So this is a finite set that's well ordered, And your operations are supposed to always reduce the complexity. Okay, so what is the complexity of a core graph? So complexity of a graph that doesn't have any hanging edges. So complexity of a finite core graph. Okay, so core graph just means no hanging trees. Okay, so this is also it's a tuple. So this is the rank of the rank of the graph, rank of the first homology of the graph, if you want. Whole graph gamma. So gamma, the point is gamma doesn't have to be connected here. And so you're just going to look at the sum of the ranks of the components. Okay? But you see, if I have a graph like this, and I erase this separating edge, I want to say the complexity went down. But first homology didn't. Right? First homology stays of rank 2, with or without this edge. But the number of components went up. And so within graphs of the same rank in the homology, I like the ones with more components better. Okay, those are simpler, because that means I erase some separating edges. So the second component in the complexity here is minus the number of components, or if you want, minus the rank of the zeroth homology. In other words, the more components you have, the smaller this number is. And I mean, maybe it's funny to have negative numbers, but the point is there are only finitely many possible values here. Doesn't matter. Okay, and the complexity of a train track, complexity of a non-degenerate train track structure. This is just the sum over all vertices of the number of gates at V, and then minus 2. Okay, so if all vertices have only 2 gates, then the complexity would be 0. That's kind of that's the simplest kind of a train track. And so like here, for instance, the complexity of the train track goes down because now I have fewer gates. Now there is a little bit something to worry about here, because it could be that this thing has only 2 gates. So its contribution to the complexity is 0, but when I perform this operation, I'll have only 1 gate, and so it's not even a non-degenerate train track. So, but then the point is, if you have 1 gate, you'll have this cleanup operation, and you lose pieces of the of delta. So this first bit will go down. Complexity of delta will go down, and then you don't care if this goes up or not. Okay, so that's why it's important to order this correctly. If you manage to reduce delta, then you don't care about the complexity of the train track or the number of edges anymore. And the other thing is that, why do we have to subtract 2 here? Well, because when you fold, so let's say maybe you have 4 gates at some point. Maybe the vertex looks like this, and then you fold a little bit. That's what we're doing over there, right? So you arrive at a picture like this. So here you have a new vertex with 2 gates, and this still has 4 gates. So it looks like I'm making it more complicated, because now I have an extra vertex with 2 gates. But this is designed so that this one actually doesn't count, because it's a 2. Okay, so anyway, so there's this, and then you can check that all these steps actually decrease this triple. If they increase something here, then they decrease something that came before. Okay, so that's how this works. Folding, right? That's you always, when you do some actual work, then usually it amounts to folding. That's how we move around outer space. How do you approximate a graph? Well, you fold somewhere a little bit. That's the sort of a standard path in outer space. Okay, maybe I should ask if there are questions. But if you don't have any experience with topology, then I would say this is kind of a typical proof where this is where you have to get your hands dirty and do some operations and then there's complexity. This is some quintessential topology proof. Okay. I wasn't going to say anything about that second half of the statement, namely arranging that vertices go to vertices. But the point is that that's really the kind of a train track that you want, because then, for instance, the issue of growth becomes just computing with matrices. You take an edge and you look at its image. It's some kind of edge path. You just have to remember how many times each edge is crossed. There's never any cancellation when you iterate, and so it just becomes some matrix calculation. And the largest eigenvalue is the growth, and you can compute it. There's the characteristic polynomial of the matrix, and that's going to tell you that this growth rate is an algebraic integer. And there's a program out there if you want. I mean, you can download it, and it's written in Sage that you put in an automorphism, and it'll give you a train track structure, train track map, or it'll tell you that it's reducible and give you some kind of relative train track map. And it'll tell you all kinds of other things. Okay. Okay, so we have 25 minutes, so maybe I'll say something about proof of 2. Number 2 is that every parabolic automorphism is reducible. And again, reducible means that there's a representative that preserves some proper subgraph. So that gives you, maybe a free factor or a collection of free factors. The subgraph doesn't have to be connected. Each component is going to represent a free factor, but let's say if it's connected, then this will give you a free factor which is invariant under the automorphism. So that sort of qualifies for being reducible. Okay. I should also say that this is not the original proof of the classification. The original proof was much more combinatorial. But this proof is motivated by one of the proofs of Thurston's theorem. So Thurston has this classification of surface homeomorphisms, and Bears gave a proof that uses Teichmüller space and complex geometry. The proof I'm giving you is really a translation of Bears' proof to outer space. We're just using outer space instead of Teichmüller space. Okay, so we have automorphism and its phi, and we assume that we have d phi is some number greater than equal to 0, and it's not realized. That's what we're assuming. That's what parabolic means. So I can take a sequence gamma I. This is going to be a sequence in CVN, so that the displacement gamma I and gamma I phi converges to d phi. Okay? So we have such a sequence. Okay, so you're supposed to imagine for this example, A goes to A, B goes to AB. Right? We have this gamma I could be the sequence of these roses where one loop is going to 0. Right? Okay, so there are two cases. Two cases to consider. Okay, the real case 1, it'll turn out that case 2 is not possible. That is, case 2 does not happen in the, it could, I could start out with a hyperbolic automorphism, and I just don't tell you it's hyperbolic, and I give you a sequence of gamma i's that maybe converge to a point in the min set. So that'll be discussed in case 2. In case 1 is that the sequence gamma I want to say the phrase leaves every thick part. Of CVN. Okay, so so every graph in CVN has an injectivity radius, which is somehow or a systole. It's the shortest non-trivial loop, right? So for example, this graph, the systole of this graph is epsilon. That's the smallest loop you see in there. So this is by definition the length of a shortest loop. This is kind of a universal definition for any kind of a metric space you can make. Like for manifolds, for Riemannian manifolds, this is a very common notion. Your systole is the length of the shortest geodesic. Here, essential, non-trivial, essential. Okay, so what I mean by this is that the systole of gamma I goes to 0 as I goes to infinity. Okay, so the shortest loops get smaller and smaller, just like in the example, right? This A was getting smaller and smaller. So in that case, I'm going to argue that the automorphism is reducible. Okay, so let's say lambda I is the slope, largest slope for, we have fi from gamma I to gamma I, representing f, and we know that lambda I is converged to lambda. This is d phi. I guess I'm calling it log lambda. Right, that's the assumption here. I'm taking a sequence of gamma i's where the displacements converge to log lambda. So the displacement is really the largest slope of this map fi that represents f. This is really the difference of markings from gamma I to gamma I phi. But I'm thinking of it as a self map representing f. Okay, so lambda goes. Well, all that matters here is that lambda I is uniformly bounded. So lambda I is less than or equal to c for every I. There's some constant that bounds all lambda i's. That's all that matters here. It doesn't matter that they converge to lambda. So we'll show that in this case the automorphism is reducible. So somehow I'll tell you in words before I write down some words. The point is that you have so some part of the graph is disappearing, going to 0. So where can this small loop go by f? Right? The slope is bounded by c. So the small loop can go to some loop of size at most c times epsilon, right? Well, when epsilon is really tiny, c times epsilon is not big enough to go over the bigger loop. So it has to go back to itself, and that's your invariant subgraph. So somehow invariant subgraphs are going to, invariant subgraph is going to be made out of small loops. Now a little complication is that you could have different scales. You could have a tiny loop and then slightly bigger loop that's still within the factor of c, and then the smallest loop can go to the slightly bigger loop. So you kind of have to figure out the scales, and you have to find a gap between different scales. When the gap is bigger than the c between two different scales, then you found an invariant subgraph. Because that's what the proof will say. Okay. Okay. So for gamma in CVN and epsilon positive, define gamma of epsilon to be the union of loops, essential loops. But here I don't require them to be immersed, so not necessarily immersed, but they have to be essential of length less than or equal to epsilon. So if I take let's say I take a graph where this loop has size epsilon half, then what is this gamma of epsilon? Well, you know, I can take epsilon half here, but then I can also take, you know, I can add epsilon half this way and epsilon half this way. Right, there is a loop of size, epsilon quarter. It's epsilon quarter because else I have to come back. Right, I go around epsilon over 2, and then I go epsilon quarter, and then I come back. And that the total is epsilon. So this red is gamma of epsilon here. So it's small loops, but then also there are some hanging trees because you don't have to immerse. You don't have to be immersed. Okay, that's the gamma of epsilon, and then let gamma of epsilon hat be the associated core graph. In other words, remove hanging trees. Hanging trees from gamma of epsilon. Right, so gamma hat of epsilon is just going to be this little loop. No hanging trees. Now, one observation is that if epsilon is less than 1 over 3n minus 3, then gamma of epsilon is certainly a proper subset of gamma. That's because this is the largest number of edges possible in a graph of rank n, so this is the average length of a graph of an edge in such a graph, and so there has to be an edge longer than this number here, and so when epsilon is less than this, you're not, none of your loops can cross this big edge. Okay, so when you're defining gamma of epsilon, you cannot get the whole graph. This big edge will not be in it. Okay, so if the number doesn't matter. If epsilon is sufficiently small, then you won't be able to. Then gamma of epsilon is a proper subgraph. Okay, so choose. So these are now our scales. We have 1 over 3n minus 3. This is bigger than epsilon, and then this is bigger than epsilon over c. I'm interested in multiplying by c every time because that's what my maps are, c Lipschitz. So epsilon over c squared, and then stop at some after say k steps. So it's epsilon over c to the k, where k is the length of the longest chain of subgraphs in the rank n graph. So so for example, k equals 3n minus 3 certainly works, because that's every time if you have a chain of subgraphs, every time you're removing an edge, and you have at most this many edges. Okay. So that's how many scales I want. And so then what do we have? So we have, so here gamma I is one of our graphs in the sequence, and I'm looking at this subset, gamma I of epsilon. This certainly contains gamma I of epsilon over c, and so on. It contains gamma I of epsilon over c to the k. And then I can also put hats. right? The associated core subgraphs will also satisfy the same inclusions. Removing trees. The core subgraph is a union of immersed loops inside the graph. That's one way to think about what the core subgraph is. And so if you have inclusion of graphs, then you get the same inclusion of core subgraphs. Okay, so this is now a chain of subgraphs. So that means that, and its length is k. So that means that there has to be equality somewhere, right? So there exists a j, so that gamma I hat of epsilon over c to the j is equal to the gamma I hat of epsilon over c to the j plus 1. So this is the desired gap in the scales, right? We have different scales, but there's a gap between this scale and this scale. There's nothing happening here. And they're off by a factor of c. And that's what we want. And the point is, this is also non-empty. This last one is non-empty for large I. This is where we're using that the systole goes to 0. There will be, for large I, there will be loops of this size. Okay, so we have this equality, but now we're done. That's going to give us the invariant subgraph, because so if fi from gamma I to gamma I has slope less than or equal to c, then it maps loops of length less than or equal to c over, or epsilon over c to the j plus 1 to loops of length less than or equal to epsilon over c to the j. Thus, so f applied to gamma I hat of epsilon over c to the j plus 1. That's the core graph. Well, that's only contained in f of gamma I of epsilon over c to the j plus 1, just because the core graph is contained in this graph. But now by this observation here, this is contained in gamma I of epsilon over c to the j. Okay, so this core graph is by f mapped to itself plus some hanging trees, right? So this is gamma I hat of epsilon over c j plus 1. I mean, I should put j, but they're equal. So j plus 1 union hanging trees. In other words, this core graph is mapped to itself plus some hanging trees. So by some, and this thing deformation retracts to the core graph. So by composing f, so after composing f with the deformation, that retracts gamma I hat epsilon over, or sorry, gamma I epsilon over c to the j to gamma I hat epsilon over cj, we have an invariant, an f invariant subgraph. And that's the end of the argument. So this is really I mean, I like this kind of argument very much, because the geometry tells you that there is an invariant subgraph. It's not really algebra. I mean, the statement is kind of algebraic, that you're looking for this invariant three-factor or something, but it's the geometry that finds it. You find a small, tiny subgraph that then has to be invariant by Lipschitz reasons. The Lipschitz maps cannot take the small thing into something big. Okay. Any questions? I should have asked that before I erased it.
you elaborate on the upper bound 3 and minus 3 and the number of edges of the graph?
Oh, then this number k here? Is this one?
3 and minus 3.
Oh, the number of edges is at most 3 and minus 3. Okay. Well, so one argument is you just think about drawing graphs. So the largest number of edges will occur when all vertices have valence 3. If you have a valence 4 vertex, then you can add more by sort of blowing up, right? If you have a valence 4, you can change it into this picture, and you get an extra edge. So valence 3 is the critical number, and then you can you can convince yourself that if you always add an edge to new vertices, the ones you didn't have before, then you're really adding 3 edges every time, because you're adding this edge, but then you're also subdividing 2 of them into this. But you can also formally do this using the Euler characteristic, right? You have the number of vertices minus number of edges is equal to 1 minus n, if n is the rank of the graph. But then also you have that 2 times the number of edges, right? This is you want to count the number of vertices. So 2 times the number of edges is equal to 3 times the number of vertices in this case. And so I think from here, right? So I don't know, 3v minus 3e is equal to 3 minus 3n. But 3v is 2e, so you get that. So minus e is equal to 3 minus 3n, and there you go. So e is 3n minus 3. If all vertices have valence 3, then this is the number of edges.
Counterpart for the curve graphing surface in our space such that the system map becomes quasi-isometric.
The system map becomes quasi-isometric. The system map from outer space to
something counterpart for curve complexing surface.
Oh, I see. There is a free factor complex. There are various complexes. Unfortunately, there's not enough lectures to talk about that. But there's something like the curve complex, and it's a complex of free factors, for example. There's actually several others where you take, if you're given a graph, then you can just take some kind of a proper subgraph, and that defines a free factor, and that gives you a coarse map to this space of free factors, which turns out to be hyperbolic, just like the curve complex. Yeah, so there's this whole other part of the theory that that corresponds to somehow Maser-Minsky, even though it's not, there are still parts missing of that in that picture, but a lot of it does exist. Okay, now I only have 5 minutes. Let's see. When does case 2 start? Must have lost a page. 13. Page 13 is missing. Oh well. Oh, there it is. Yeah. Well, okay. I don't know if maybe I'll just say it slightly quicker. So the case 2 is that the sequence gamma I stays in a thick part. In other words, the systole of gamma I is greater than or equal to epsilon for all I. So in that case, you actually so here we'll argue that phi is actually hyperbolic. Okay, it's not parabolic. In other words, that the displacement is realized. Okay, so here's the idea. So I want to, if you want a quick slogan, it's going to be Gromov-Hausdorff convergence, if you're familiar with what that means. So for the moment, we can forget markings. So forget markings for the moment. And then after a subsequence, all gamma i's will be homeomorphic to each other. There are only finitely many homeomorphism types. So after a subsequence, all gamma I are homeomorphic and can be represented by points in a simplex. You know, like in a simplex in outer space, right? If they're all, say, theta graphs, then I have 3 numbers here, and I can just draw them all in this simplex with some missing faces. You know, so I have the sequence of gamma i's, and there's some points in this fixed simplex. And after a subsequence, I can assume they converge. So after a subsequence, gamma i's converge to some graph gamma. So there's some graph gamma, and there's a sequence gamma I that's given to me, and it converges to this gamma. Now, it couldn't be that gamma is in the missing phase, because that corresponds to some loop going to 0. And we're assuming that all the loops have definite size. Okay, so this is where we're using that it's in the thick part. And but it could be that gamma is on the proper phase, right? That's a slight complication. The gamma could have a different homeomorphism type, because some edge could collapse. Like the theta can collapse to rows. Okay, but so we have these representatives. Fi from gamma I to gamma I of slope, you know, lambda I converging to lambda, which is the, you know, so d phi is log lambda. And then we also have these maps, difference of marking maps between gamma and gamma I. So we have gamma to gamma I and gamma I to gamma. Maybe I'll call them, I don't know, this is hi and gi or something. And these are difference of marking maps. And their slope goes to 1. Okay, that's another thing I didn't really elaborate on, but this technically this uses the continuity of the Lipschitz metric with respect to the weak topology. You see, these are points in the simplex in outer space, and I'm just saying that the distance between gamma I and gamma goes to 0. Okay, that's continuity of the Lipschitz distance. This is true, and I didn't emphasize it in these talks. But that's just so. The way to say this is that there are these difference of marking maps where the slope converges to 1, right? Because the distance is log of the slope that goes to 0. So then I have this kind of a diagram. Here's gamma I. I really want, the gamma is where, I'm going to show that gamma is in the min set. So I want to map from gamma to gamma. And the way I'll get it is by composing this way, right? So I have from gamma to gamma I go by hi, and from gamma I to gamma I go by gi. And then here I have fi, and then here I just take the composition. And the slope here will also go to, you know, this is hi, fi, gi, and the slope of gi, fi, hi also goes to lambda. All right, because these are hi and gi go to 1, and fi goes to lambda. Okay, now I can say Arcella-Ascoli, and these things will converge. So Arcella-Ascoli, these things will converge to a map from gamma. This converges to some map, say capital F, from gamma to gamma, and it has a slope of f is equal to lambda. In the limit, you get slope lambda. Okay, now you have to put markings back in the picture, and maybe that's the part I want. It's not hard, but maybe that's not maybe the way to finish the lecture with thinking about markings. But there is some, you know, these gamma i's are secretly marked, and then you can think of gamma as being marked by the compositions here. And that gives you a representative with this with the right slope, and so that means that phi is hyperbolic. And that's a contradiction. Okay. So that's it.